Okay, it's good to see everyone again today. So today we're going to review a concept from high school algebra, or perhaps your first calculus class, called difference quotients. So the basic formula for difference quotient, before I explain what they are, is as follows. Delta y divided by delta x is going to be equal to f of x1 minus f of x sub 0 divided by delta x, where delta x is defined as x1 minus x0. So what does this equation tell us? You shouldn't just memorize this equation, right? That's not very useful, and you're not going to learn a lot from this. It's much more useful to understand what this equation is trying to tell us, and then you won't have to memorize it. You'll understand where it's derived from. So this equation is assuming we have that y is a function of x. And just as an example, let's look at a situation where y is a function of x. Let's say we have a function that looks at something like this, maybe. Right, where y is an increasing function of x. And we have 2 points along the x-axis, point x0 and point x1. x1 can be smaller or larger than x0. It doesn't matter, but just for this example, x1 is larger. And for any given value of x, you can plug in that value of x into the function, and the function outputs a value of y. So when we input the value of x0, we get a function of y0 equal to f of x0. And when we input the value of x sub 1 into the function, we get y1 is equal to f of x1. Okay, so we have 2 points. Essentially, we have 2 points along this function. Right, this function is labeled f of x. So what the difference quotient is telling us is it's giving us a ratio of the increase in y. This delta y is right here. It's the increase in y that results, or it should be the change in y that resulted from the increase in x. This is delta x right here. So what this is telling us is it's telling us the slope of the line running in between these 2 points. If we zoom in here a little bit, if we draw a straight line that runs exactly through these 2 points, oh, that was a pretty good line. What we have here is the difference quotient is telling us the rise over the run, right? So coming back, delta y is the rise. It's by how much we're going up along the vertical axis, and delta x is the run. It tells us how much we're moving along the horizontal axis. So what the difference quotient is telling us is it's telling us the slope of the line that runs in between these 2 points. And this is important because by dividing the change in y over the change in x, what we're getting is what the difference quotient tells us is the average change in y as a result of a unit change in x. But it's adding one more caveat, that this average only really applies in the small part of the function of the curve that we're looking at. So the part of the curve that we're looking at is this one right here. We're only looking at the part of the curve in between x0 and x1. We're not really considering the part of the curves before x0 or after x0. We're just looking at the average rate of change in between x0 and x1. when we plug those values into the function to get the curve and the resulting y values. So while it is useful, it tells us the average change in y, it's limited because we can only ever look at a small part of the function for any given calculation. But it's useful if you just want to explore the average slope, the average change in y for a unit increase in x for some portion of the function. Okay, so that's it. That's basically it for difference quotients. And just to reiterate, delta y is given by f of x1 minus f of x0, and you divide all that by delta x. Okay, so pretty soon I'm going to post a quick review of the first derivative and trying to connect the concept of difference quotients to the concept of the first derivative.